Welcome to day 8, the fundamental theorem of calculus. This is an important day. We're going to tie together what we've been doing with antiderivatives and understand how it applies to what we're trying to do in real life applications and even in graphs in general. So we're going to go through this example. A car going 50 feet per second breaks to stop in 5 seconds. Let's determine the total distance. And using geometry, we made this graph. So here's a graph, and because it's constant deceleration, my acceleration is change in velocity over change in time, which is negative 50 over 5, or negative 10 feet per second squared. So that's actually the slope of this line. The acceleration is negative 10, and that's the slope of this line. And then when we found the total distance, the distance was just the area under the curve. Well, if that's the slope of the line, that the equation of this line is v equals negative 10 t plus 50. But let's go back to finding the area. Area equals 1/2 base times height, which is 1/2 times 5 times 50. And my area, which is my distance, is equal to 125 feet. That was using geometry. Now let's go back into looking at how we do it using antiderivatives. So using antiderivatives, I'm going to start with my acceleration of negative 10. My velocity is the antiderivative of a, which is the antiderivative of negative 10 dt, which is negative 10 t plus c. But at t equals 0, my velocity equals 50. So my velocity equation is negative 10 t plus 50. And then my distance equation is going to be the antiderivative of velocity, which is negative 10 t plus 50 dt, which is going to be negative 5 t squared plus 50 t plus c. But at t equals 0, my distance is 0, so that becomes a c. So my distance equation is negative 5t squared plus 50t. And I know it takes t equals 5 seconds for it to stop. So d of 5 is equal to negative 5 times 5 squared plus 50 times 5. I get my distance as 125 feet, which is exactly the same what I had before. Okay, this was using the antiderivative. So the whole point is that this antiderivative of this velocity equation, which is what my distance is, was equal to the area under the graph of my velocity. Okay? And that's the idea. This is what we're going to look at. Is that when I take the antiderivative of something, it turns out to be the area under the curve. So that last problem wasn't so bad because all I had to do was find area of a triangle. So I could have used geometry. But not every curve is going to be a nice geometric figure, such as if I wanted to find this area, that I'm going to do right here underneath this curve. I want all this area. I can't use geometry. That's no shape I have a formula for. So the idea is that this area will equal the antiderivative of this function, whatever the equation of the function is, going from point A to point B, using these as my x's. So now we're going to put little numbers with this integral sign. A is called the lower limit, B is called the upper limit. So the fundamental theorem of calculus, FTC for short, where little f is the derivative of capital F, so that means capital F is the antiderivative of my original f of x function. And I'm going to put numbers in. I'm going to put these x values in. A and b are x values. So it says the integral, or the antiderivative, from a to b, lower to upper, of my original function f of x is equal to capital f of b minus capital F of a. And all we're doing is plugging in these numbers into the antiderivative. A is the lower limit, b is the upper limit, and when we have numbers in here, what we've been doing before when we were doing the antiderivative, those were called indefinite integrals. When we put in limits, a and b, this is called the definite integral. We're finding an actual value. And when I do this, the integral will be the area under the curve f of x between the x values a and b, where above the x-axis is positive area, and below the x-axis is negative area. Okay, so let's go through an example. So I'm trying to find the area between x equals 1 and x equals 4 underneath this parabola. Okay, obviously there's no geometric formula for area here. So I'm going to have to use my calculus skills that we just learned about how we do antiderivatives to find area. Well, the antiderivative of this is going to be 1/3 x cubed, and I don't do a plus c any longer. I only do a plus c when I don't have limits, but as soon as I put these numbers in, the 1 and the 4, that means I have a definite integral, no more plus c. What I do now is I make a vertical line, and I put the numbers 1 and 4. Okay? And 4 is the upper, 1 is the lower, and I'm always doing upper minus lower. So it's going to be 1/3 of 4 cubed minus 1/3 1 cubed, because I'm always doing upper limit minus lower limit. And I put this in my calculator, and I get 64/3 minus 1/3. And I get, this is 63/3. And that means this integral from 1 through 4 of x squared dx is equal to exactly 21 units. So this area here in pink is equal to exactly 21 units, which is the same as if I had a 3x7 rectangle. Why I say 3x7? Because this base is 3. So if I went up to 7 and do a 3x7 rectangle, can you see that this pink area is exactly the same as this orange rectangle, that this extra pink maybe fills in this stuff that isn't filled in? But we had to use calculus to do it because there's no geometric formula for area with a parabola. Okay, we're going to find out the areas of these two problems. First we'll use geometry. So for part A, which is over here, this is a nice triangle. And so area equals 1/2 base times height, and from 4 to 6, so my area equals 1/2 times 6 times, well, this height, the height here is just this y value, and that's 3. So I get this area is equal to 9. Well, now I'm going to actually use my calculus to show that it's going to be 9. So I set up my antiderivative. I'm going to take it, it's going to be 1/4 x squared minus 2x And since there's no plus c because I have a definite integral of 4 to 10, so I'm going to put in my vertical line 4 to 10, my upper and lower limits, which means I need to plug them in. So 1/4 10 squared minus 2 times 10. That is the whole upper limit. Minus my plug in 4, 1/4 4 squared minus 2 times 4. And that's my whole lower limit. Well, I get 100, so I get 25 minus 20, so equals 5, minus, I get 16, so it's 4, minus 8, 5 minus a negative 4, which is equal to 9. So I get exactly the same result that I had earlier. Now let's do the second problem. I'll pick red. So this is a trapezoid. So I have to do area is 1/2 the height and then the sum of the two bases, where this is the height because the trapezoid is based on the parallel sides being bases. So A equals 1/2. This height here is equal to 4 times 4. Oops. Times 4. And this base here is -1 plus this base on the other side is -3. I get area equals 1/2 times 4 times -4. So I get an area is equal to -8. And the reason why it's negative is because it's below the x-axis. Well, let's do the same thing on this next. I've set my antiderivative. I've already taken it already. This part is not going to change. It's going to be equal 1/4 x squared minus 2x, except where I evaluate it's going to be different. I'm going to use 2 and -2, my upper and lower, so it's always upper minus lower. 1/4 2 squared minus 2 times 2. That's my upper, minus 1/4 -2 squared minus 2 times -2. That's my lower. Move it up a little bit. 4, this is 1 minus 4, so this is -3 minus this is 1 plus 4, this is minus 5. I do get an area equal to -8. So I get exactly the same result as before, but using calculus. The only reason I could use geometry because these shapes are geometric figures. Okay, so how do we apply it? Well, what I want to do from A to B, that's from this point here to this point here, and this area is just this positive area, 0.8. What I want to do from A to C, well, that'll be the integral from A to B plus the integral from B to C. So I'm just really adding these things together, and from A to B I just found it was 0.8 plus from B to C it's -2.6 because it's below the x-axis. So I get a total value equal to -1.8. And then finally, this, well, not finally, this next one, from A to D, is from beginning to the end, so it would be the integral from A plus B, plus integral from B plus C plus D. So if I add up all the pieces together, I get 0.8 plus a -2.6 plus a 1.5, and my total value at the end is -0.3. And then if I want to do B to D, that would just be from B to C plus from C to D, and that would equal -2.6 because it's below, plus 1.5 because it's above, and I get negative 1.1 is the antiderivative or the integral for those values, but actually the area between those points. So I'm going to use this figure on the right. What's nice about this, it's all very geometric. I could break it up into pieces, into rectangles and squares. And this first area here is negative a half. This one is negative 1. This one is negative 1. This one is negative a half because they're all below. This one is positive a half. This one is 1. So when I want to go from 0 through 4, from 0 through 4, all I have to do is add up all these negative areas. I get negative 3. When I want to go from 4 to 6, I'm going from here to here. All I have to do is add up all these positive areas. I get 1.5. When I want to go from 2 to 6, from 2 to 6, I'm adding up these and these. And if I notice, they basically all cancel. I get my area is 0 because I get negative 1.5 negative area and plus 1.5 positive area. If I want to do the whole thing, 0 through 6, well, over here I have negative 3. Over here I have positive 1.5. I add them all together. I get negative 1.5 is a total area. There's more negative area than positive area. Okay, let's actually use the FTC. So when I take the antiderivative of this, I get 1/3 x cubed plus 2x squared plus 3x. No plus c because I have limits. I put a vertical line. My upper is 3, my lower is 0. Gotta love plugging in 0. I'm going to plug in 3 here. I get equals 1/3 3 cubed plus 2 times 3 squared plus 3 times 3 minus, when I plug in 0, I think you could see that when I plug in 0 I get a bunch of zeros. 27 over 3 is 9, plus 9 times 2 is 18, plus 9. So I get this is equal to 36. I'm going to do the same thing here. I might have to rewrite this. X to the 1/2 dx, and when I take its antiderivative, I get x to the 3/2, but now the reciprocal is 2/3. I'm plugging in 0 and 4. Actually, let me put it nice so you can see it better. Plugging in 0 and 4, and when I plug that in, I get 2/3 of 4 to the 3/2, which is my upper, minus 2/3 times 0 to the 3/2, which is my lower. And when I plug in upper minus lower, well, 4 to the 3/2, 4 to the 1/2 is 2, to the 3, that's it. So this is 8. So I get 16 over 3 minus 0, which is just 16 over 3. That's what I get for that one. Not so hard. It's just a bunch of plugging in numbers. Now this last problem is a little bit different because it's asking what is the area between this graph and the x-axis. So I should know what this graph looks like, but first maybe I should factor it. So if I factor it, I get x minus 1, x minus 7. I set that equal to 0, and I got my x-intercepts of 1 and 7. So actually I'm going to erase this. One and 7. So this graph looks like this. And we're trying to find this area between 1 and 7. So it's just the integral between 1 and 7 of the function that was given to you. And then you take its antiderivative, which is going to be 1/3 x cubed minus 4x squared plus 7x. And I'm evaluating it between 7 and 1. So I plug in 7. 1/3 7 cubed minus 4, 7 squared plus 7 times 7. Minus, now I plug in 1, 1/3 1 cubed minus 4 times 1 plus 7 times 1. This is my upper minus my lower. That's what I do every single time. And I plug things into the calculator. And I get negative 98 over 3 minus 10 over 3, which is negative 108 over 3. I get negative 36. So this area is equal to negative 36, and it should be negative because it is below the x-axis.